Good morning, everyone, and welcome to the new chapter of Boston Plastic Recycling webinar series. This fourth chapter will be related to plastic sampling processes and outcomes. So today's agenda, the first part, we're going to explain a little bit the objective of this kind of webinars and the speaker's presentation. Afterwards, I will explain quickly the objectives of the Primus project. Afterwards, we will have Mathilde Taveau explaining the pre-100 quality recycling. Then we will have the plastic sampling processes and outcomes by Mathilde and Jarkko. At the end of the webinar, we will have some questions as roundtable for both the speakers. And in the last point, we'll have some attendees questions. So in this webinar, you as attendee have the camera and the microphone off. So please, if you have any question in any part of the webinar, just write it down in the chat and we will translate those questions at the end of the webinar to the speakers. Okay, so I don't know if you can see my camera because it seems that it's freezed. It's freezed. Okay, so I will. Okay, now I think.
Yeah.
Thank you. Okay, so for the first part, I would like to explain what is the objective of this Boosting Plastic Recycling webinar series. This is a series of webinars that are focused on unraveling the latest updates and good practices of plastic recycling. So these webinars are boosted by the Primus project with close collaboration with other R&D projects. And in this case, we are going to explain in this occasion just the processes that we are having in the Primus project. So the Primus project is a European project that is funded by the European Commission, and I will explain a little bit more about the Primus project for you to know. And the main objective of this webinar is that we are going to analyze how to prove compliance with product legislation and explore plastic sampling techniques in order to achieve a high quality recycling of the plastic. So to introduce myself, I'm Carolina Mejia, Senior Innovation Project Manager at Mondragon Corporation, and in the Primus project, I manage communication, dissemination, and exploitation. I have a background degree in architecture, master in urbanism, innovation, and project management, and I have been working in the past 7 years in R&D technologies and innovation projects, such as the Primus project. And we have today two special guests that are part of the Primus project as well. We have Mathilde Taveau. She's a regulatory affairs manager at Plastic Recyclers Europe. In the Primus project, we have the chance to have her as our regulatory work package leader. She holds a master in chemical engineering, specialized in materials and processes. Her graduation research on the development of polypropylene recyclates from old household appliances led her to the plastic recycling world. After working as a plastic engineer at a WE recycling facility, she is now focused on the chemical legislation as well as on R&D projects at Plastic Recyclers Europe. So welcome, Mathilde, and thank you for being here with us.
Thank you.
And we also have another special guest that is Jarkko Saarinen. He is a professor and scientist manager at University of Eastern Finland. We also have the chance to have him in the Primus project as Primus characterization work package leader. He holds a PhD in physics and in technology. He has acted as a professor of materials chemistry and engineering at the University of Eastern Finland in Joensuu, Finland since 2018. He has co-authored more than 80 scientific peer-reviewed articles dealing with nanomaterials characterization and applications with more than 20 years of research experience. Thank you, Jarkko, for being here. And well,
yeah, thank you.
thank you. So they will be presenting afterwards the two parts, but here I would like to explain quickly what is the objective of the Primus project. The Primus project is a European project that wants to improve the plastic recycling industry, creating new polymer technologies for recycling the polymers for automotive and home appliances. So we have 4 demo cases in the Primus project, 2 for the automotive sector and automotive cooling circuit. The third one, refrigerator to refrigerator. The fourth pilot, washing machine door seal. And these are our 4 pilots. Do we have a problem? Okay. Afterwards, here we had the. Can you see the map?
Mhm.
Well, we are 12 organizations in different countries, in 6 countries, and we started in May to 2021, and we are in the middle of the project right now. We have 1 year and a half left of the project. So we want to create in this Primus project a quality and safe recyclate, support the use of recycled plastics as safe raw materials. Then we want to demonstrate the application on the 4 demo cases that I already mentioned in automotive and home appliances, and support recyclate market with debromination pretreatments and analytics. So if you don't have, if you haven't had the chance to join our community, we have 2 communities, an industrial community and another one for citizens. So you can, if you're interested, you can check our webpage and join our stakeholder community or our newsletter to have more news about our project. And here you can see the partners that we have in the Primus project. We have VTT, the University of Eastern Finland, Plastic Recycler Europe, the University of Tallinn, Green Delta, Mondragon Corporation that I represent, Circularize, Coolrec, Meyer, MTC, and Cicaucho. So moving forward, just remember that if you have any question, you can write it down in the chat and we will translate all the questions to the speakers at the end of the session. Okay, so for the first part of our agenda, we will start with the explanation of pre-100 about quality recycling. For this part, we have invited Mathilde Taveau. Mathilde, please take control of the presentation and the floor is yours.
Yes. Thank you very much, Carolina, for the introduction, and welcome everyone from my side. So as the first part, we're going to talk about the PRE 1000 tool and especially related to quality. So the PRE 1000 tool is a tool that has been developed in order to monitor the substances of concern that may be present in a recycled plastic. So this is really a tool that is meant to verify if the materials, so the recyclates, are compliant with the chemicals legislation, so the product legislation. So this is here really we are placed at the end of the recycling process where we will test really the recyclates. So if I go to the next slide, the first thing I want to bring forward is why do we have sometimes some SVHC, which are the substances of very high concern in the material? Well, we have some substances mainly because of the lifetime of the article. This is what is bring here in the slide. So if you have a material that has been, let's say, produced in 2005, then you can have a material that contains, for example, here I took the example of flame retardants. which is a substance. A substance group that is meant really to prevent that an article is going on fire and making a lot of flame. So this is the purpose of this, and it has been used in many type of electronic devices. Here I took the example of a hairdryer, but this is the case for many different electronic devices. And the point is like this are often added because of fire safety norms, and therefore it has been added for a specific purpose. But the thing is, like, once this device has been used, so here for a couple of years, a decade, and then the hairdryer at some point went broken. And then this is where you brought it to the container park, and it's arriving afterwards at the recycling facility. The thing is, like, this material and this device still contain some substances. And those substances are included in material that arrive at the recycling facility. Let's say that in the meantime, during all those years, if the specific substance that has been added in this product is getting restricted, it means that then it's up to the recycler to ensure that this new material that they will produce, so the recycled plastic, do not contain this specific substance that is restricted above a certain threshold, so above a certain limit. And this is what is explained here, because then the recycler has to sort the material, and technically to have a fraction of material that would be compliant and a fraction non-compliant that then would be sent to disposal. But it's important that the material that is placed again on the market is compliant with the chemicals legislation into force. So this is a little bit the background that you need to understand, and this is the reason why it's important after to monitor the recycled plastic that are placed on the market in order to ensure this compliance. Because of the long life service of the article, it happens that indeed the input material still contains some substances, even if they're banned and even if the recycler, of course, did not put them in the material themselves. They're just inherited from the past, let's say. So the key problem, as I said, is really on the product lifetime. So it depends on the kind of application. For example, if you take packaging, you have a very short lifetime of the article. But if you take building and construction, it can go up to 50 years because a building is going to stay really a long time, even more. So this is the range of the different lifetime that can be a problem, because then it means that the compliance with the chemical legislation can be quite tricky to reach in some specific recycled plastic and waste stream. And this is why this monitoring of the substances is very important to ensure the compliance. So indeed, this banned substance can continue to find its way into the waste stream, even though it has not been added and it's not used anymore in the industry. And the job of the recycler then is to find the best environmentally sound management of this plastic waste stream, meaning that you have to sort it properly so that you really have a fraction in the end that will be compliant with this product legislation. What is done currently in the different recycling process, and especially here if we take the example of the electronic devices, so the waste from electrical and electronic equipment, and especially this shredder light fraction, which is the plastic fraction, but still contains, let's say, a lot of different impurities. This fraction is usually placed in a sink float bath. So this is a bath that has been set at a very specific density, and you have to know that the plastic that are contaminated with, for example, flame retardants, such as a brominated flame retardant, which was quite heavy elements, and the bromine element is a heavy element. So it's going to change the density of your plastic, and instead of being at the same density of your intrinsic polymer, then it's going to be at higher density, meaning that if you put a bath at a specific density, then it's sinking. So then you can really separate the plastic that are sinking that would contain some brominated flame retardant from the one that are floating that will not contain those substances, and therefore can be recovered afterwards. The plastic that are sinking and that are containing the substance are then sent to disposal. Here, this is what you see in the drawing on the left. So you really have a fraction that floats, then that's the product fraction that is compliant with the 500 ppm of PBDs, which is a brominated flame retardant, or rather a category of brominated flame retardant. And then you have a waste fraction. The waste fraction is the fraction that is sinking, and therefore it's sent to disposal because here it would be considered as a waste. This is what you can see also on the right. This is the process like a little bit explained in more detail, really the sink float. What is happening here is that you have, let's say, some plastic particles. So I would say at the beginning, they're roughly between 2 and 3 centimeters of diameter, or it's rather a square maybe. And what you have is like they're placed in the hopper, then they're entering the sink float bath, then there is a mixing process to ensure that all the flakes are really, let's say, placed homogeneously in the bath, and then you really have the separation process through the resting time, and then you have the 2 fractions that are exiting the bath. And then what we will check now is the monitoring of the substances that is placed then on the product fraction, so the green fraction that you see here, because this is the one that will be placed back on the market. So this is necessary that this is the one that complies with the product legislation. So now up to the method. First, we have to check what are the relevant chemical legislation that will apply to recycled plastics. In that case, the first one that is mentioned here is the REACH legislation. So it's a chemical legislation. Here we have the substances of very high concern. Those substances, they're not strictly prohibited. It is mandatory to provide information if you have a substance that is above 0.1 threshold. This means that indeed, in order to have a statement saying that you're below or above 0.1, it means that you have to test the concentration of the substances in order to know whether you're below or above. So this is the first thing, but it means that you can still place the material on the market if you're above, but you have the obligation to inform your customer that this is the case. Then in REACH, we have a second part, which is the restriction. So the risk restriction here, it's a different procedure, let's say, because here it's specific for a substance, but then the substance will be banned. It means that you have a threshold, and above the threshold, then you will not be able to place it on the market unless there is a specific derogation that applies. And usually they are spotted when there is, or they're entering the legislation when there is an EU-wide risk toward the use of this substance. A third legislation that is quite relevant is the POP regulation. The POP regulation lists the persistent organic pollutant. Those substances, they are first included in, let's say, a broad convention, which is the Stockholm Convention. That's more at global level. And then they're included in the POPs regulation, which is at EU level. And in the POPs, we have 2 types of limits that are applicable. The UTC, which is the unintentional trace contaminant limit. That's a limit that the product needs to comply, so really the output. And then you have the low pop content limit, which is there on the waste. And this waste, if you have a substance that is above this low pop content limit, then the waste needs to be destroyed, and therefore it needs to go to incineration. And last but not least, another one that is included also in the monitoring tool is the ROS. So the restriction of hazardous substances, but this is only dedicated if the recycled plastic goes back into electronics. So for example, if you put it back in a hairdryer, for example, then in that case, you would have to comply with the ROS directive. In that case. And these substances that are listed here, they are also on the tool, included in the tool. So now let's look more precisely into this tool. So the point is, at the very beginning of using this tool, you have to specify what you're testing. especially in terms of input stream, because there may be different substances that are used in different articles, of course, and therefore specifying the waste stream is already giving an information to which type of substances could be present in the input material. And the second point is like there is also the output that needs to be specified, so the polymer stream, because there is also some substances that are polymer specific. That we will see a bit more afterwards, but this is quite relevant to inputs. Then, of course, so here we talk also about the sampling, and we will see a bit more about this afterwards, but the sampling is very important. It should be performed in a way that it's representative and sufficiently well done so that the result afterwards are accurate. This is quite important. And the key is the homogenization of heterogeneous material. And this we'll see also a bit afterwards. How can we make the material quite homogeneous so we can have an analysis in the end that is quite relevant. The process flow of this monitoring tool is first inputting the product definition, then having a sampling protocol, of course, to take the flakes or the pellets that are tested, then the sample preparation. How can we prepare the sample so that we can test afterwards for the different analysis? Like here we have mentioned XRF, which is on the elemental composition and the chemical analysis that Jarkko will mention a little bit more afterwards. And then how to report. So of course, this information is very often relevant for the customer or for the downstream user of the material. And therefore, it's important also to report to this actor in the value chain so that everyone is informed and the communication throughout the value chain is working. Then if we look at the overall approach, so how we have taken those substances, because, you know, if we take all the legislation that I have talked about before, there is for sure a lot of them that makes like, yeah, at least now I put like 240 substances, but there is probably a bit more. The thing is, how can we reduce the number of substances to analyze to avoid analyzing more than 200 substances? As soon as you reduce the number of substances to analyze, first, it's easier because you know what you're looking for. And second, it's also cheaper because you don't have to look for the whole range of substances. The first thing that we have done for this tool and in order to select the right substances is a literature review. So we have checked the different physical chemical properties, the technical function, additivation rates, evidence of historic use, polymer specificity, proof of absence of the different substances that are listed in the legislation to check whether they can be present or not in specific recyclates. Then we move on to the second step, which is on the XRF screening. So how can we eliminate some more substances based on the elemental composition of the material? And last but not least, if we still have some substances that we have not eliminated throughout the first two steps of the process, we do some analytical testing, and then we check that indeed the material is compliant, and of course, or if it's not compliant. So for the first part, I put here two examples because it's always easier to have some example to understand properly what has been done, especially for the literature review. So here, if we take the two examples on the chemical and physical properties, there is some substances, for example, that are not compatible with plastics. We can especially look here at the boiling point of the substance, because you know that during the plastic production, you have very often an extrusion process. This extrusion process goes at very high temperature. So if you have a very low boiling point, it means that the substance cannot be present in plastic, in the end plastic, let's say, or in the article in high concentration. And I mean by high concentration, concentration above the threshold that is listed in the different legislation. So this is the first point on how to eliminate substances. Here, this is only an example, so there is many different processes that have been done. And then the second one is on the polymer specificity. So there is some additive that are used in one polymer, but will not be functional in another polymer. And therefore, this way we can rule out some additive or some substances from certain polymer and only add them in other polymer when they're tested so that this substance is quantified. For instance, if we look at lead stabilizer, they're used in PVC. So this is a substance that is necessary to test in PVC, but not in other streams. So this is, for example, one point that has been added there. Then, once the literature review has been done, we move on to another part, which is the XRF screening. XRF is a tool that is present in quite some recycler facility. This is also why it has been chosen, because since it's a monitoring, it's important to be used in practice, of course. So this is good if it's a practical tool that is already implemented. If we look at the different substances of concern, they tend to have some specific elements, so chemical elements. Here I listed a few, so the bromine, chlorine, lead, cadmium. And here what we have to take into consideration is that XRF is assessing this elemental composition. So here, the thing is, in the legislation, you have the concentration in substances. So it means that here, what you see on the right side of the slide is that we assess in the legislation the concentration of the complete molecule. But the complete molecule cannot be tested via XRF because XRF is only testing the elements. So if we look at this molecule, it means that it would assess the concentration of the bromine elements within the material, but it will not give you the concentration of the complete substance in the material. And this is why we need to do a conversion in order to test and to compare with the proper value, because it would be like if you compare gram and a completely different unit, but then you would not be comparing something that is comparable. And here, this is the same thing that we have to do. So if we take the example of the DKBDE, which is the brominated flame retardant we talked about before, here we have a threshold at 500 ppm. The molecule, if you assess it, it contains 83.3% of bromine by mass. This you can calculate it by the mass of the bromine atoms over the mass of the complete molecule. And then you obtain this. If you apply this ratio and this percentage to the limit, then you obtain a new one, which is 417 ppm of bromine. And therefore, here, this is the new point where you have to compare. So what we have done in this tool is that we have done all the calculation automatically. So automatically, when the XRF results are inputted in the tool, then you have a direct comparison with the new threshold that is calculated. So this is how it works. And then once this step of XRF has been done, then you reduce again the number of substances that are present. And then you arrive to the last point, which is the remaining substances, and then the analytical testing. So here I will not develop because Jarkko will talk about it afterwards, but technically we can perform some analytical chemistry test in order to assess the concentration of the molecule, so really the substance, and you know, like roughly how much concentration is present for a substance in your material, and therefore you can comply whether the material is compliant with the legislation or not. So this is on the testing. So last but not least, what are the key messages? Of course, the PRE 1000 method is meant to be applicable as a monitoring. So it means that the more data is generated on this material, the more you will know about the compliance on the long term of the material. We know that we can have some variation sometimes. So it's also important to apply this method regularly so that it's really becoming of added value. So it's really enabling the recycler to assess those substances of concern in a cost-effective and reliable manner. This is quite important. And it was really designed to be applicable on the long term. It's also meant to monitor and to track the different substances that could be present and to really build trust in the recyclates. So by knowing more about this compliance, it's also important then to state to the customer that, okay, the material is compliant, it's safe to use, and we don't have to question anymore the plastic recyclates. And it's increasing the credibility throughout the value chain. So we have like really a proactive approach to the plastic industry because of this testing of substances. So for this first part, this is it from me. So thank you very much. Of course, all the questions, as Carolina said, you can write them in the chat. And then I think this is also for me to begin with.
Yes.
So yeah.
Yeah, Mathilde, you can continue. Please take the floor. This is the second part of the whole explanation in our agenda is about plastic sampling processes and outcomes. So Mathilde will explain a little bit more of the plastic sampling techniques. And afterwards, Jarkko will explain one of those techniques that is used in the Primus project.
Thank you very much, Carolina. So here, a very brief explanation, mainly related to the work that we are doing in the Primus project, because we are investigating this monitoring, of course, of substances, and also the sampling process and analysis. So here I will mention a little bit on the sampling process, and then Jarkko will go on the analysis. So what we are aiming to do in the Primus project is to define a good sampling strategy in order to test the substances afterwards, both in terms of XRF, but in terms of analytical testing after. As I said before, so the sampling is really key, especially when we perform the different type of analysis, whether it is on characterization of material with mechanical properties, rheological properties, but also elemental composition, monitoring of contaminants. I mean, there is plenty of analysis that we can do on recycled plastics for sure. And a good sampling process is leading to the accuracy of the result after. So it's very nice to have a tool that is giving accurate results, but if we do not have a representative sample, the accuracy of the result will not be good. So this is important to relate the two of them. It's both on the sampling and the sample preparation. Those are very important. So what have we done here in the Primus project in order to assess this sampling is to take some material that, let's say, is made material, so it's not recycled plastic, to really mimic what would happen in terms of homogeneity in the end. So let me explain. What we have done is we have created some flakes. We have created some flakes that do not contain any substances and some flakes that contain some substances. And then we have mixed them at different ratio, but a known ratio. And then we have done some specific sampling scenario, different scenario. And then we will do an analysis in order to check which scenario is first the most practical and second the most representative, because we will test throughout the sample if we have an homogeneous repartition of the different contaminants that have been included. So we have also tested with different contaminants, especially color, to really have a visual aspect, and then some contaminants like here that are contaminated with specific substances. What is the aim of this? The aim is really to have in the end an homogeneous sample to find the most robust methods. In order to have a good result in the end, we need a robust sampling method. We also need to think that this method will be implemented in practice at the plastic recyclers. So we do not want a fancy method that cannot be applicable with very fancy tools. We need something that is practical so that we are sure that the people that will be sampling the material will be able to use it. So this is quite important. And we want to ensure, of course, the repeatability of the experiments. So what we do, as I said before, and we are really working on flakes, because then we are really mimicking what is happening on the sampling process at the recycling facility. So this is the first thing that is important. The second thing is at the moment, I cannot share the result first because we have not completed the study yet. But once the study will be finalized, then we will share the high-level results as part of the Primus project because it will be beneficial to most of us. So we will check which one is the scenario that is the most appropriate. And then this is also something that we plan to implement in the PRE 1000 methods to really enhance the accuracy of the result afterwards and to have more accuracy on the compliance or non-compliance of the recyclates to the product legislation. So that being said, I will give the floor to Jarkko, I think, because I think it's his slide now. So Jarkko, you can take control, and thank you very much.
Thank you very much, Mathilde, for the presentation, and I will continue going through our bits and pieces for the Primus project. So I come from the University of Eastern Finland, and we have for many decades been dedicated to the mass spectrometry analysis, and we have very good infrastructure for doing the ultra high resolution analysis, which can be applied for various different fields. And here in the Primus project, we are doing this for characterization of plastics and also especially for the recycled plastic streams. So then let's go on. So here are the examples of the mass spectrometry devices that we have here in our Joensuu campus. So the main workhorse that we use in the Primus project is the Bruker timsTOF, which is the trapped ion mobility time of flight mass spectrometer displayed here on the top image. What we have here as a benefit for this recycled plastics is that we can very easily apply very small amount of material and then run very quick tests on which we get a still very high resolution image on the different compounds. We can even distinguish between different structural isomers and conformers in this one. And we have very high mass resolution also in the timsTOF device, so 70,000 full width at half maximum, and also very high mass accuracy, so less than 1 ppm amount of substances we can detect from the matrix. So in the case that we do need to go on to even more detailed analysis, for example, in the case of niaces or then substances of very high concern, if we want to do a more detailed look about those materials, then we can go on to our high magnetic field 12 Tesla Bruker unit, which is a Fourier transform ion cyclotron resonance mass spectrometer. And then as we take a look about the differences in the mass resolution, so here we can go to about 1 million in the full width at half maximum resolution. The mass accuracy is 100 times more sensitive than what we have in the timsTOF. And then also the sensitivity that we can detect is in the picogram level with the high field unit. But still, it is worth to emphasize that the timsTOF device is a very high resolution machine that can be applied in most of the analysis. I would say that it's more about the scientific interest that we go on than for the 12 Tesla unit. The typical analytical workflow that are possible with the infrastructure that we have available here is explained here. So we do have a lot of different possibilities, what type of analysis we can run with these devices. In this Primus project, we are also studying the volatiles that are emitted during the processing of recycled plastics. So this is something that we are also analyzing using our headspace unit in the mass spectrometers. But mainly what we have been using in this project is the one that is here at the bottom. So the solid feedstock being the recycled plastics and virgin plastics. So we use the direct inlet probe, so which allows us to take the plastic sample directly to be analyzed. Then we typically use the atmospheric pressure chemical ionization for these samples, and then they are analyzed using our timsTOF device. So what are the typical spectrum that we get from the timsTOF measurements? So for the plastic samples, we have developed a protocol. So we use a temperature ramp up from the 150 C up to 450 C in 50 centigrade steps. The measurement time is roughly 10 minutes. So we stay 90 seconds at each of the steps. And then the sampling rate of our timsTOF device is 50 Hertz. So every second we collect 50 different mass spectra out of the sample. So on the top image here, we have the total ion count of the high impact polystyrene. So we do see that once we increase the temperature, then the total ion count is increased as the thermal degradation starts to play a role. And then we can, from each of these different points, as we collect the data, we can then go on and take a look about what is the mass spectrum distribution of different compounds that are emitted at these different temperature points. So here, as an example, is an ensemble of the 450C emission. So in the case of high impact polystyrene, what we typically see is we have the emissions of the styrene dimers here in 207, then the trimer in 312, and then the multiple compounds of the styrene units. And also what is important is that typically, mass spectrometric tools are considered to be only qualitative in nature, but then we can also do quantification of compounds, at least on the semi-quantitative stage. So this is something that we have also been developing within the Primus project. So one example here, what's the difference between the timsTOF and then the high magnetic field FTICR system. So as mentioned, the resolution on the FTICR is significantly higher. In this case, 100 times higher. And here's an example of the 395 mass over charge peak. And one can clearly see here the difference between the resolution of the timsTOF and FTICR. So FTICR having much narrower peaks, and also one can identify different peaks that one cannot see in the timsTOF spectrum because it's a convolution and having a lower resolution. But it's still worth emphasizing that this timsTOF device is very well suitable for the plastics analysis. So how do we do then the typical setup for the measurement using the direct inlet probe with the atmospheric pressure chemical ionization tools in our timsTOF device? So as Mathilde said, the representativeness of the samples, especially in the case of recycled plastics, can be difficult. So what we have been doing is we have been grinding the polymer samples using the centrifugal mill. And the typical sample mass that we use in our measurements is roughly 1 milligram. So here on the left-hand side, you can see the typical glass capillaries that are used for the direct inlet probe. So we apply a quartz filter at the end of the capillary to prevent the samples to be immediately ejected from the capillary. So then this one is applied into the ion source, and then they are ionized and then analyzed. So very small amounts of samples can be used. Actually, in this picture, we can also use material from the plastic sample that is just simply a piece of plastic that is fitted into the quartz filter. And you can see the size of the quartz, the capillary compared to the matchstick in this image. So then once it's embedded into the direct inlet probe, then it's ionized, and then we analyze it using our timsTOF device. So here's an example of the pure ABS polymer. On the top image, we have the typical total ion count spectrum that we gain from the measurement using the temperature ramp from 150 to 450 C. And then here at the bottom image, we have then the mass spectra at the 450 C, and what we see from the ABS. So we do see that there is a combination of different constituent components of the ABS. So there is a styrene component, then there's the butadiene component, and then acrylonitrile component, and the different mixtures of them. So here seeing the SA, SAA, and SSA combinations, and all others as well. So this is a very typical spectrum that we get from the polymer sample. As Mathilde mentioned, one of the targets that we have here in this project, in the Primus project, is the analysis of the brominated flame retardants. Here's an example spectrum of one of the widely used BFR, being the tetrabromo bisphenol A, the TBBA. And we used a similar protocol as we have done for the polymer samples. so going from the 150 to 450, and then here's an example around 300 degrees. What are the typical mass spectra that we get out of the TPBA? So what we have here is that the 543, we have the intact TPBA that is emitted, and then we also have the different components. There is a dibromo and dimethyl components, and also the thermal fragments that are emitted as the TPBA starts to degrade at the 300 centigrades. And then we have also done samples on which we have a known amount of the TPBA mixed together with, in this case, high impact polystyrene. So from 1,000 to 10,000 to 100,000 ppm of bromine content. And then typically, how do we do the quantification in the mass spectrometry is that in the case of polystyrene, then everything is then interrelated to the PS dimer signal. So if we go at the 207, compared to the TPBA signal at the 543. So in the case of 1000 ppm bromine content, we see that the PS dimer peak is the most representative peak on the spectrum. And then as we increase the amount of the TPBA, then the relative content of the TPBA is increased compared to the PS dimer peak, as one would expect. And by doing this relative signal strength, we can also do semi-quantification of the amount of these substances in the sample. And then also here at the bottom is an example of the more detailed spectrum for the 1000 ppm around the 545 mass over charge ratio. And as what we can conclude is that we can get high quality semi-quantitative data with very low noise level can be acquired using the mass spectrometry tools. So the characterization protocol for the polymer sample. So if we receive an unknown polymer sample, so what we typically do is we do a cryogenic grinding, and then we use our direct inlet probe together with the timsTOF device. And what we can gain is this qualitative data and also semi-quantitative data of the different compounds that are present in the sample. This is suitable for all ionizable compounds. They can all be detected, and then this is also suitable for non-targeted analysis. So as we get the mass spectra over the very wide range, then we can identify the different compounds at the very small amounts present in the sample. So then in the case that there are compounds that we need to quantify, then we can go on for the targeted analysis, doing a Soxhlet extraction of these materials, and then we can go on for the quantitative GCMS analysis to get the actual accurate amount of how much of these compounds are present in the samples. So to conclude and to summarize the characterization part, so in this Primus project, we have been developing the mass spectrometry tools, the sampling and analysis protocol for the timsTOF device, so that we can do the temperature ramp from 150 C to 450 C. And within the measurement time of 10 minutes, we can very accurately detect the different compounds in an unknown recycled plastic sample. So very detailed identification of different substances, such as brominated flame retardants, substances of concern and very high concern, and also the non-intentional added substances can be detected. As mentioned, the quantification can be done for selected compounds, and then also we can achieve a significantly higher resolution using our 12 Tesla FTIC in the case that is needed. So this is my last slide. So I would like to thank you all for the attention. If you have any questions, just drop a question at the chat. And our another professor from the University of Eastern Finland, Professor Janne Jänis, he's our professor of organic chemistry, and he has been running the mass spectrometry research for the past 10-15 years here at our department. But if you have any questions, just let us know, and we will answer that one. And I will give the control now back to Carolina. Carolina, can you take the control over this one?
Oh,
Okay.
sorry, it seems that I was having some troubles with the Microsoft Teams. Okay, thank you, Jarkko, and thank you, Mathilde, for that explanation. I think that the mass spectrometry technique that we are using in the Primus project is quite a good technique to understand how to recycle the plastic a little bit better. Now we have a roundtable session where we have 3 questions for you both to answer. I don't know if you could activate your camera and your microphones. Thank you. So, so for the first question, and the main idea is that you both interact.
Carolina,
Yes.
there was a question in the chat.
Yes, we will.
So okay, so we will take those at the end of this one. Is
Yes.
that correct?
Yes, that's correct.
Okay, thank you. Sorry.
All the questions at the end. No worries, but it seems that it's related with your presentation, Jarkko. So, going back to the round table, we have a first question. The main idea of this round table is that you both could answer the having both perspectives, the technical part and the regulations perspective as well. So the first question that we have for you is, what are the best practices for manufacturers and recyclers regarding plastic sampling? And I think that Mathilde could answer this one better.
Yes. Thank you, Carolina, for the question. So, best practice. So this is something that we try to define in the Primus project, actually, on finding the best sampling strategy that we could apply, especially for recycled plastic. But what I would give as a first advice is always to take a big sample, mainly from different big bag of the production. That's always a good point. And then to take all of those small samples, mix them together, reduce them, and then trying to make this fraction, especially if it's flakes, homogeneous. So this can be done throughout several processes, but a process that involves melting of the material is always very good, because then you're sure that even all those flakes are mixed together. And then if there is a potential substance of concern or any other type of elemental composition that you would like to analyze and so on, then it's more spread and homogeneous throughout your sample. Also, if we talk in terms of XRF, for example, we often have those handheld XRF. It's very easy to use if you're on a plane surface. So having this type of, injection molding bars, for example, dog bone specimen is always very nice, especially if you have them for other purposes. If you test mechanical properties, for example, that's very relevant to have. So I would say, like, the overall approach would be this one, and then of course stay tuned to the result of the Primus project, because we hope that we will have a clear sampling strategy to bring forward to recyclers.
And I could comment on my side this one, that so in the Primus project we have these ultra high resolution mass spectrometers that we can use for the identification of different compounds. So once we are taking a from a very large amount of materials examples, and then these contaminants can also be very much diluted, but still we can see them accurately using our high resolution tools. So we are not expecting that people would use the high resolution tools on a daily basis, but then we are just building up the suitable protocol to ensure that one can use, for example, with the handheld XRFs to run the analysis.
Yeah, and maybe just one thing to add based on this is that often we have a big gap between the volume that we produce in a plastic recycling facility and the amount of material to analyze in a chemical analysis. So I think this is why all those steps are very necessary on how we reduce the sample, so that in the end, the gram that we analyze in the chemical analysis is still sufficiently representative of the tonnage that we produce at the plastic recycling facility. So it's really filling this gap with a proper sampling strategy that is necessary to have something that would be accurate in the end.
Thank you both, and I think that the summary at the end of two is quite relevant. And in the Primus project, we are having or searching for the best practice for this plastic sampling. So, as Mathilde said, stay tuned with the results of the project. Then for the second question, we have, should we use the same sampling technique for all type of polymers or different ones?
So I think the first thing that we need to distinguish here is that it heavily depends on the type of recycled stream that we are using, what type of sampling technique we need to do, and then also the sampling techniques. We have been mainly using here the cryogenic grinding, and we are now doing together with the Primus project. So we are developing the different sampling protocols that could be the most that would result in the most representative sample of the plastic stream.
Yeah.
Mathilde, could you complement
Yeah,
on your side?
definitely. Yeah, I can completely echo what you have said. Yeah, what we see is that the substances that we test, it's strongly related, as I said before, to the type of waste stream and the type of polymer that we are using. But I would say in that case, it's mostly related to the waste stream rather than the polymer. Or at least, yeah, in our opinion. Because in the end, it's also depending on how much experience you gain on your material. Let's say if you do the monitoring of substances like the PRE 1000 and you do this through time many times, and then you see that you always end up with the same results, then it's already giving you a lot of feedback on your sampling strategy, whether this is the good one or you should take another one. Then it's also depending on the shape of your material. If you have flakes, or if you have pellets, or if you have, I don't know, like powder, all of this is influencing a lot. Like the particle size is very important in sampling strategies. So I think there is a lot of parameters that can indeed change, but I would not say that the polymer is necessarily one. But indeed, it's very important to take into consideration all the different bits and pieces before building your own strategy.
I have a question over there, Mathilde. Then you have to have a sampling technique strategy for each of the streams, even though it's the same polymer. For instance, it's a polypropylene, and the stream could come from different industries. Should you have a new sampling technique and strategy for each of the streams?
I would say not necessarily, but it's also depending like how much potential flakes that are contaminated are gonna end up in your stream. So based on this, like based on the outliers that you can find, you have to define whether you have to take a big volume or a smaller volume. So that I would say like the technique per se and the different steps will not change, but the volume to take in input can vary based on the type of contaminants that you may have in your material.
Okay. Okay, perfect. Then for the third question in the roundtable, what other value can high resolution characterization bring to recycled plastics, Jarkko?
Okay, so I think one of the biggest benefits, since we can detect very low levels of compounds. So what we can do with the high resolution spectroscopy is that we can guarantee the safety of the recyclates. And this is something that we are building on within the Primus project. And then also the second thing is that there is a direct link to the legislation with the high resolution characterization. And I think Mathilde can comment on that one.
Yeah. Yeah, actually, like all the work that we are doing here is technically related to the chemicals legislation. So I think it's important to take it into consideration. What is in the chemical legislation is some threshold. Those thresholds are getting lower and lower and lower. So this is important also to improve the analytical techniques so that we can meet those thresholds in order to state the compliance of the recycled plastic with the chemical legislation. As I said, this is also part of the PRE 1000 tool, where in the end, in order to eliminate the remaining substances, we do some characterization analytical testing. And then in that case, it would be very, very relevant because we can reach lower concentration, but we can also detect when there is not necessarily that much, let's say, quantity of substances that are inside. So it's indeed very relevant for the legislation and the compliance. I think you're muted, Carolina.
Yes, I was muted. I'm sorry. It seems that I'm having troubles with Microsoft Teams today. Thank you both for answering these questions. I think that these questions led the attendees other questions. So now we're moving forward to the attendees questions. And Etienne is going to share her screen. So maybe I will stop sharing. Okay. Now we can see your screen here, and she will translate I will transfer the question.
Okay. So the first one, are plastic recyclers expected to run this high precision instrumental analysis equipment on premises? Because it seems highly qualified personnel is needed for it.
This will be for Jarkko. No, and
Jarkko.
for the mass spectrometry part.
Okay.
Yeah, sure. We do not expect that every recycler will have a timsTOF device on their facility because, well, actually, to run the measurement is rather straightforward. You just apply the sample into the device, and it will give you the mass spectrum. But then doing the analysis of these results is rather demanding, and then also the devices are expensive. But what we are building here in the Primus project is that we are using these ones as an additional tools to guarantee that the protocols that we are developing, for example, that are based on the use of XRF, so we can guarantee that these protocols that are developed and used are doing the task that they are supposed to do.
Okay, thank you. Yeah, this is an extra part of the project.
On the next question, using the same sampling technique, should the analytic methods be the same for all types of polymers?
And this is related to the second question of different sample techniques for different polymers or waste streams. I think this could be for you, Mathilde.
I think this is more towards Jarkko. On the analytical techniques.
So if you consider our devices that we use, in principle, it doesn't make a big difference what type of polymer we are having. So the temperature ramp-up program that we have developed seems to be working very nicely for all of these polymers that we have been studying in the Primus project. So in principle, if you're using mass spectrometry tools, then you can identify these different compounds very easily and straightforwardly using the similar type of approach. But as we discussed with the sampling techniques for the different polymers, then certainly the quality of the waste stream should be taken into account.
Yeah, maybe just one thing that I thought about in the meantime. When we talk about the XRF, For example, you have in that case some influence of the polymer matrix in when you do the analysis. So if you take a PVC matrix or if you take an ABS, PVC will have a lot of let's say background because of the chlorine content that there is in the material. So there you would need a specific, let's say, program in order to really put back this background and to have an accurate analysis. So in that case, you would have to change a little bit some things. But it depends on the different like analytical tools that you're using.
All right. There's another 2 questions in the chat. So the next one, do we need to look out for further recycling codes for certain bio-based plastics, for example, cellulose and PLA, to improve segregating and sampling of polymers? Any comments about the regulatory measures for bioplastics?
Yes, I can try to answer this one. So at the moment, there is some files ongoing at EU level on bio-based and biodegradable plastics. The thing is, at the moment, indeed, there is not a dedicated stream, so it's ending up in the stream, the common stream of plastics. And it tends to be quite an impurity for certain stream. So at the moment, it's not really well sorted. So indeed, having a proper, let's say, stream for those type of material would be maybe good, because at the moment it's not necessarily recycled. I mean, at industrial scale. So yeah, some work is definitely needed on this field in order to improve the context surrounding this type of material.
They're still working on it.
Okay, thank you, Mathilde. And for the last question, a recycler that receives material from different streams should analyze each of them, or the result of the mixing of all of those, with the same nature?
I think this question was similar to the one I asked, but Jarkko, please.
Yes, I can comment on that one. So to improve the reliability and representativeness of the samples, then in principle, certainly it will be beneficial if the different streams are analyzed separately, and then also one can take a quick analysis on the mixing of those, all of those material streams combined together. So depending also certainly also from which types of streams you are using in your process, if you need to analyze them separately, or then is it sufficient just to go on for the mixed one? And this is also one of the things that we are tackling now with our samplings that is ongoing in the Primus project.
Yes. Okay, thank you. I think we don't have any other question. Maybe you can move forward to this last slide. Okay, so thank you all for being here. Thank you, Jarkko. Thank you, Mathilde, for being with us and sharing your knowledge. Please, for all the attendees, if you like to know a little bit more of the Primus project, know the results that we will have in the next month, please join our community, or you can join the industrial or the citizen community. And if you want to have more information about it, you can join our newsletter as well. So stay tuned. This webinar is recorded and will be published in our YouTube channel as well as in our webpage. And thank you all. Bye. Bye, Mathilde.
Thank you. Bye-bye.
Thank you.
Bye.
Thank you. Bye-bye.
Bye.